Hello, my name is Barrett Moody, and welcome to Physics 2211 Lab 2 Projectile Motion. So the purpose of this lab was to analyze the motion of an object in two dimensions moving in a parabolic path because it is what is also known as projectile motion. We then made two computational models that displayed the projected displacement of the object and compared this to the actual displacement in the XY plane with resistance, one computational model with resistance and one without a resistance. The fundamental principles in this lab apply to Newton's second law, pertaining to how a system's change in momentum is equal to the net force divided by the mass. And this pertained to how the ball accelerated in the y direction due to the force of gravity. The other fundamental principles was the gravitational force, which I was just previously explaining, and the drag force. And the drag force is due to air resistance caused by the air particles that catch on the paper ball and push it in the opposite direction. For our procedure, we started by recording a paper ball and slightly in the horizontal direction, besides a meter stick, and the meter stick served as our reference point. And then in this scenario, our paper ball is a system, and the meter stick, as well as like the wall, are the surroundings. And we use the app Tracker to help analyze data, get data from analyzing the motion of the paper ball. And here's that motion of the paper ball, which we then put into Tracker. Then our data from Tracker gave us a spit. It's not the smoothest line, which we will get into when we talk about our sources of error, but this is a line of the motion that it gave us with the x displacement on the x-axis and the y displacement on the y-axis. So this is our glow script model without drag, and the first thing that we changed was the position vectors of where our ball started and the initial ball's velocity, which we got from the Tracker app and the data we got from the Tracker app. We then changed our value of t from when the time started and the time interval that we got from 1 every about 60 seconds in Tracker, which is how we got our t values. And then we changed the equation for F net, which is equal to gravity, which we also have on the left-hand side of the code. And we had a position and velocity update formula, which helped display the Tracker data in the computational model using the code. Then our computational model with drag was exactly the same except for two things. One of them is we changed our B value, and the B value is the value of how much air resistance is occurring. And once you take that value and multiply it by velocity squared, that will give you the net force or the force of drag in the opposite direction of gravity. So we estimated our B value to be about 0.0014, and then we updated our F net vector to include that B value right there. When it came time to compare our computational model and observed data, we got results which we expected to get. We can see the red line here is our computational model without drag, and we can see that we expect it to travel further, which we would expect because there's no net force in the opposite direction slowing it down, whereas the blue and the black lines are the computational model with drag as well as the Tracker data, and we can see those align with each other much better than the red line, which is without drag. However, there are still sources of error, particularly pertaining to the Tracker data, which we saw a rough jagged line rather than the smooth curved line from our computational models. It was still accurate in getting an answer which we expected. However, some sources of error are still present due to that Tracker app, and as well as estimating our B value to be 0.0014 rather than there's no good way to calculate it. Moving on to the question portion of the lab, asking what does it mean when it is talked about terminal velocity. So terminal velocity occurs at the moment when a free-falling object experiences a zero net force, meaning that the object is falling at a constant rate because their drag force and force of gravity are equal. So once those two forces are equal in an opposite direction, the object moves at a constant velocity. So our computational model that predicts a terminal velocity as the acceleration begins to plateau with more time, meaning the net force is approaching zero, and that's our computational model with drag, because the drag will continually increase as the velocity increases, which will change our net force. Lastly, for our what if questions, if the object were originally thrown up with the same initial speed, would the time the object takes to reach the table be the same, longer, or shorter than the time it took in our original experiment? And we know that it would be longer simply due to kinematics. We can see in this equation where d, in this case, would be like h, the height of where we threw the ball. We know that it'll eventually reach a height of 0 when it touches the table, and it is currently at a height of 1 meter before we let it go. And if we throw it straight up, it would have a positive velocity going in the positive y direction, while the force of gravity acts in the negative y direction. So we can see that the positive velocity will just simply give us more time.